This brings us towards the end of the 90s and actually into the next decade of the 2000s. And Dave Maurer is going to talk to us about that. Dave was a student graduating in 2000 on HBTEP, but then stayed for 12 years, being almost never left, but has in fact moved on to join the faculty at the University of Auburn just in the last year. But Dave, of course, has an experience here that's beyond just being a PhD student, but also continuing and in fact serving as the main scientist on HBTEP as it's run throughout the last decade. So Dave.
Thank you. So I guess I'm the new blood, or part of the new blood, actually. It was really kind of a new generation of students that came in the mid-90s. Let me put up, this is what the machine looked like in the early 90s. It was a lot cleaner and kind of more pristine than it currently is. And luckily it still works well. I actually did my undergraduate work at the University of Wisconsin at Madison, and I got into plasma physics. I worked for Stuart Prager on MST as an undergraduate, and a professor from Columbia was actually visiting, giving a seminar, and I was contemplating going to graduate school at that time, and Stuart introduced me, and that happened to be Jerry. And number one, I thought it was cool that you took the time, because I was some little undergraduate kind of schlep. I mean, I was nobody, but you sat down and we talked, I think, for half an hour, 45 minutes, and it sounded like there was a lot of neat things going on at Columbia. The machine had really just started operation, and it had a movable conducting wall inside, which as an experimentalist that sounds kind of crazy, and sounded very exciting. And so when I first got here, which was in 92 or 93, I think I was the last plasma lab graduate student to actually have the pleasure of having Bob teach physics of fluids to me. He retired not too shortly after. And the text that he used for it was Landau and Lifshitz text on fluid mechanics. And I can honestly say, Bob, if I know any fluid mechanics, it's due to you. Not to Landau or to Lifshitz, because that's quite an imposing book. I was also lucky in my first year, when you typically take only classes. I did a little work in the lab. I was lucky that I had Plasma 1 and Plasma 2 was taught by Amitava before he had left. And I still remember to this day, I still have the notes. In CGS, unfortunately, but that's because you're a theorist. And I still remember that when Plasma 1 started, he came in and he delivered these beautiful lectures. And he started out by saying that, well, this is an MHD place, and you're going to learn MHD. You'll have to, because that's what you'll be studying and working on, most likely, for your thesis. And so what I'm going to do is I'm going to force you to learn kinetic theory. And so we spent the whole first semester going through Fokker-Planck theory and the Rosenbluth potentials, and we even started with the n-particle distribution function and all these things that if I ever have to teach it, I'll have that in the back of my head, so thank you. So let me get back to the experiment. So when I arrived, HBT had just started. It was on maybe shot, 1,500 or so. And those were the days where you still didn't quite know how to run the machine. We were trying to figure out how to make plasmas, how to make discharges. For all the graduate students now, all these kind of canonical ways of making current ramps to generate kink modes, or making a high beta plasma with a little more initial start current. Those were all invented back then. So it was a very exciting time. I remember coming from Madison, I was actually a little bit worried, because Columbia was kind of a smaller program. Madison is a big place. MST, there's programs in nuclear engineering and in electrical engineering. And when I got here, I think it was clear. There was a lot going on. There was HBT, there was the linear machine, CTX had started, Tom Marshall's FEL was still ongoing, and so even though the faculty was smaller, it was a very vibrant, kind of alive place. And it was a fun place to be working in. I would not say that, life in the plasma lab was never glamorous. This is Ray Kumbarji hauling out garbage to one of the dumpsters. These are things that sometimes you have to do. And it actually made me very happy because it's just like being back in Wisconsin. We would do similar things. And so I felt at home. So this is, Dave just showed this picture. This is the HBT group when I got here. This is actually a picture from a paper that Tom Ivers published from an invited talk in 1994, showing the top of the machine. And in the 90s, really the research themes were kind of two. It was ideal wall kink stabilization. And then later on, in the end of the 90s, and this is what I worked on and some other people that I see out in the audience, we got into more tearing mode physics before we started the resistive wall work that took place in most of the 2000s. And so this led to a whole series of PhDs in the 90s. I think it's actually kind of a tribute that you would have people graduate essentially every year or two for a small experiment like this. And one of the things that I've taken with me, and I remember first coming here, and I really hadn't done anything. And people were gracious enough to actually put my name on one of the first papers, because it's such a small group that your output isn't enormous. And so the spirit of that we were a team making this experiment work was always there, and it was something that I try to continue in my new position now. So this is, I have to show some data. I mean, this is, being a physicist. Looking back at the 90s, I think this was one of the really interesting results. And this was in an invited talk by Tom Ivers. And using this movable wall, you were able to actually stabilize the ideal kink mode. And so here we're showing pictures of the tokamak with the shells retracted, shells inserted. The top shows the plasma current ramping up, and in green is the edge Q, and as that comes down to 3, from standard MHD theory, you see large M is equal to 3 oscillations on external magnetic coils that would lead to the destruction of the plasma. And by pushing in this wall into this close-fitting configuration, you would see that you would still see some hash, and there was still some rumbling going on inside of the plasma, but it would live through that period that destroyed the plasma when the shells were retracted. I'm going to highlight one more piece of data from the 90s because I can see him in the back audience, Dave Nadel. So we kind of switched gears from the kink mode research and investigated more tearing mode type modes. And so here we're showing the first measurements of what's called the feedback phase instability timescale, where you apply rotating fields to the plasma. There's a little pre-existing mode, and it locks to it in a phase where it gets larger in amplitude. And then you actually flip the phase quickly by 180 into what would be the feedback phase. And you see that the mode realigns back to the locked phase where it wants to grow. And this is a very fast time scale and would limit the use of at least magnetic feedback for classical tearing modes, for example. Later in the 90s, I think it was clear, or becoming clear with the discovery of neoclassical tearing modes in the 90s on TFTR and elsewhere, that using magnetic coils to actually do feedback on tearing modes was, while you could do interesting physics with it, was probably not the way to go. So that kind of gets us to the 2000s. I'm going through this a little bit rapidly. So now you can see there's a kind of a nice clutter of diagnostics. There's a Thomson scattering system over on the far side, and various probes as the machine was maturing, and the graduate students were working hard and building new diagnostics. And that takes us into, so this is my transition. I was going to sit and then come back up. I got, and that leads us to the resistive wall mode years, I guess you could call them. And a question here was, how do you stabilize the slowly growing kink mode that is present when you stabilize the ideal mode, but because of resistive diffusion, you can have the plasma slowly kink. And this was one idea, and these are things that you can do on a small experiment. You just go and you get a graduate student, and we wind coils on the back of a stainless steel shell, and the idea was to try to make this look superconducting. So you actually had a feedback coil and then a concentric sensor, which was smaller, and you could sense the flux of the mode leaking through the wall, and then with some electronics, apply an appropriately phased voltage to drive a current on the coil and try to null that field out, kind of attacking the mode at its very definition almost, that it's this slowly growing mode with flux diffusing through the wall. And that actually worked, and that was also published in the year 2000 or 2001 by Corey Cates. And then in the later years, during the 2000s, this is after I had transitioned to being a research scientist, which is interesting. I guess there's a few comments there. It was interesting staying in the same lab and actually doing that, because there's a continuity of graduate students. And so when you turn into a research scientist, it turns out the graduate students that you actually worked with never listen to you. You have to wait for a new generation, and then you can kind of talk to them, and they'll listen to you a little bit, sometimes. And so Corey and Mikhail were there when I was still in graduate school, and they never really listened. But Alex did, and Yuhan, and I think Oksana, you did sometimes. And so essentially, every few years on HBT, we would rip out the wall and install a new wall to investigate new physics. That's how, you might be asking the question, how is a 20-year-old machine kept going? And although in many of the years in getting ready to write proposals, we did say, boy, we got to build a new machine. It seemed like there was always something to still investigate, something to still try to understand with the device that we had. And I think that's actually still true today. And so these, over the course of the years, we've had several more invited talks, and we've still kept up, I think, with about a graduate student or two per year getting out. And so that leads to almost the current day, at least experimentally. Just before I left, we installed a new wall, and you can tell that our graphics have gotten much superior from the 90s here. And so this was just recently installed, I guess 2 years ago, by people in the audience who are smiling, hopefully. And it's just a picture of installing it. Everyone working hard in our clean suits, getting ready to put this inside the vacuum chamber. And here's a picture of the group of people that actually accomplished it, with some inside photos of the new conducting wall, structure, and sensor coil arrays. And I guess with that, that's kind of the historical portion of the talk. So let me, I guess, sum up Sorry if this has been a bit of a stream of consciousness. That's because it is. Thought up on the plane flight here. I think that there's a couple words of wisdom that I've taken from my time here. And one is from Jerry, which I discussed with you earlier today. And he told me when I was a young graduate student that don't build it, buy it if you can. And, you know, being an experimentalist, we're kind of tinkerers, and we like to build things, and I never quite understood that, and I still like to build things, but I think I've learned my lesson after 20 years or so that it's better to actually build it. See, it's a Freudian slip there. That it's actually better to buy it than to build it. The other person that I want to thank is David Gates. Because I was his baby graduate student when I came into the lab. Dave was the senior. He was like the head honcho, and he thinks that he built the Thompson scattering system by himself, but he did have a little help. I can't say that I enjoyed it at the time. And in the ensuing years, building yet another Thompson scattering system that didn't quite work, and then finally getting it right. The current one that we have been using, so there was a big learning curve there, and it was actually a very humbling experience. You know, you think you're going to get something done quickly, and then it's years later. But with that said, that was actually one of the reasons that I got my current position. Is that I have Thompson scattering experience, and I'm going to build a new Thompson scattering system for CTH at Auburn. And so I guess I'm not sure if I should quote Nietzsche, you know, that which does not destroy you makes you stronger, or, you know, you might not always get what you want, but you get what you need. It could be, you know, either Nietzsche or the Stones, I guess. So I think with that, I'll say thank you.